Dr. Patino, huh?
Yeah.
I know his papers, man. Here you go. Welcome. Yeah. There you go. How you doing, guys? Good? I know. Okay. It's a bit, yeah, it's kind of cold. When is it? When is your Hyder's exam?
Friday.
Friday?
7 a.m.
Oh, great. I'm actually gonna gear up from now. Okay, good. So how's the volume, by the way? Is everyone good? Everyone hear me? Okay, yeah. Oh, you just came, didn't you? Whoa, did I miss you? How did that happen? Really? I'm so sorry. Here you go.
Thank you.
Yes, welcome.
What function do you have?
Yeah, if you know me at all, yeah. Hey.
Thank you.
Welcome. You can give this back to me by the end of the session today. Okay. That's good. By the way, if anyone notices that the screen needs to be moved or I need to move the paper, just let me know. I'll try to do my best with that, but sometimes it's going to slip, so, okay. Well. Hmm? Do I what?
Do you want a room mic?
A room mic?
Yeah, room mic is like everyone can hear you, like speakers are on here. Do you want to do that or are you good?
What do you think?
Up to you. Or do you loudspeaker or soft?
I'm speak like this usually.
Okay, so do you want a mic?
Sure, why not? By the way, who just came in? How many people just came in? You did? You too? Or, okay, gotcha. This is Chem 2045.
Yeah, okay.
Okay, sounds good. You can give this to me at the end of the session. Okay. Are you in Hyder?
Yeah.
Sounds good. Hey man, make sure you fill this out and you can give it to me at the end of the session. two mics? Let's try that out.
This is for live streaming, and this one is for the room itself.
All right. Gonna put them this. Do they interfere?
I don't think so.
Let's hope not.
Speak something.
Hey, is this better? Can you guys hear me better, or is it the same?
You're gonna have
Better.
to put it here now.
More?
Yeah, put it up here somewhere.
I can't see, but let's give it a shot. Oh,
Probably turns more.
how about this? It's fun. You're close, so the. All right, how many people just walked in? You two in the back? Don't worry, I'll come to you. I gave you one, right? Yeah. Hi. You came in? Awesome. All right, man. Just fill this out, and by the end of the session, you can give it to me. Okay. I'll actually come and take them from you guys. Time? Are we good? Start? I can start? Yeah. Okay. All right, hey guys. My name is Sam Abad, and I'm the Chem 2045 tutor. So as far as I know, there are Dr. Patino and Dr. Hyder teaching this course. So I just want to make sure everyone's in the right class. Are you all good? All right. So obviously today is going to be live streamed. And also make sure you fill out your the surveys that I just handed out, and I'll pick them up at the end of this session. And I hope you guys printed out the review packet that I have. Basically what I'll be going over is, as much as I can, a comprehensive overview of this whole course. And we'll start all the way from chapter 1, doing sig figs. We're going to do a lot more than that for sure. But we're going to start easy. And then we'll climb up to all the different reactions that we have to do, like acid-base or combustion. We're going to do calorimetry. So let's get started. So I'm going to start chapter 1. This is just a very small overview of the basic things when we're looking at an element. Obviously, when you look at the periodic table, you're going to find the X, and that could be any element. Sodium, potassium, lithium, right? So if I pull up a periodic table here, X can be any element, like this one that I just highlighted, okay? And you guys know that by now. Your atomic number is going to be the Z. Your mass number is going to be the A. And you got to know that, long ago the periodic table was actually based on the mass number, but now it's based on increasing atomic number. And the atomic number, aka the proton number, is going to be what makes the atom unique. So no two atoms are going to have the same number of protons. If they do, then we're talking about the same element. Sounds good? That's just the basics. And just to re-emphasize, atomic number, ooh. There we go. Atomic number is also known as the proton number, and this number gives the atom its unique identity, okay? Now, if you have a neutral atom, then the proton number is going to be equal to the electron number. That's only if you have a neutral atom. Now, what happens if you don't have a neutral atom? Let's say you have an ion. We learned about cations and anions in this course. Then if you have a cation or an anion, you're going to have a different number of electrons than the number of protons. So, let me give you a quick example. We look at this periodic table. Let's say I pick lithium. Actually, you know what? It doesn't really matter. So let's say I pick lithium. The 3 down here is going to be your proton number. If it's a neutral atom, how many electrons are we going to have? It's going to be 3 as well, right? Knowing that lithium is an alkali metal, we know it's going to have an ion of +1, right? So it's going to have 1 less electron. We'll talk about that in a second, but I just wanted to point that out. Okay. Let's talk about the N, which you don't see when you're looking at the element. N, right here, is going to be your neutron number. This number determines whether you have an isotope or not. Okay. So let me go back to the mass number right here. Okay. The mass number is made out of the proton number and the neutron. Okay. So isotopes differ in their neutron number. So do you think that isotopes will have a different mass number? Logically speaking, yes. Because the mass number is made out of the proton and the neutron. So if isotopes have different neutron numbers, then of course the atom is going to have a different mass number as well. So all isotopes differ in their number of neutrons, and they also differ in their number of, or the mass number. Okay. Now I want to draw your attention to something that is found here in the periodic table. I don't know if you can see that on the screen, so I'm going to bring this up. But do you see this? Oxygen, the number right here, 15.999. This is the mass number as we know it, right? The molar mass, or the atomic mass, or the atomic weight. All these are synonymous terms, right? What's important to know about this is not just the mass number of oxygen. We're talking about all the isotopes of oxygen that are found and their percent abundances in the universe are taken in account in order to actually determine this mass number. Okay. More on that later. And by the way, I'm gonna end up, finishing around 15 minutes early, so you guys can ask me direct questions or maybe specific questions. So if you have any questions, write them down so you can, remember them, and feel free to ask me. Other than that, if there's anything very, very important, then raise your hand and I'll know that it's important. Other than that, I assume it's not an important question until the last 15 minutes. Okay? All right. So, pure substances. Pure substances are matter that have distinct properties and a composition that does not vary from sample to sample. Okay? A pure substance can technically be an element, or it can be a compound. Okay? So an example here I put is water. Water is H2O. Water will always be H2O wherever you find it in the universe. That's never going to change. And table salt, NaCl, will always be like that as well. Okay? So this is what I meant with elements. Elements, in essence, are really substances that can't be broken down any further. Right? They can't be broken down into any simpler substances. And a prime example of that is all the elements on the periodic table. A compound now is a substance that's composed of 2 or more elements, like water, which we just mentioned, right? Water is made out of 2 hydrogens and 1 oxygen. Okay. I want to move on to mixtures. Mixtures are created when there is a mixture of compounds and elements together. That's worded funny. But basically what you need to know is that mixtures can be uniform or homogeneous. We also call homogeneous mixtures as solutions. Okay, gotta know this. And what that means in essence is that they're uniform throughout. So if I take a sample of air, okay, on a rough estimate, it's going to have 20% oxygen, some 70-ish% nitrogen, okay, on average. That's going to be almost a constant composition of air, okay. Now cereal, that's a representation of a heterogeneous mixture. What do I mean by that? That means if I take a random sample or a random, spoonful of cereal, I'm going to have a different composition. For example, I like cranberry and granola in my cereal, right? And a given spoonful of it, I might have a different amount of cranberries than granola, right? That's what makes it a heterogeneous mixture, okay? And this is just, the basics. I kind of wanted to start with something that you guys already know, you're very comfortable with, so that once we build up as we go throughout the session, you're kind of warmed up, okay? So let's move to the next thing. I want you guys to remember your Diatomic Seven. This is important as it will be repeatedly coming up in the next chapters that we talk about. A nice way I like to remember my Diatomic Seven is actually in the way they actually form the number 7 on the periodic table. So I'm going to start with oxygen. I'm going to go to fluorine. And I'm going to go all the way to iodine. So that's 1, 2, 3, 4, 5. Oh, hydrogen is also going to be the exception. Okay. And sorry, that should have spread to nitrogen. Okay. So diatomic sevens make a 7 on the periodic table plus hydrogen. This means that in nature, when you find hydrogen by itself, it's never found like this. At least, usually. It's going to be found by itself like this, as a diatom. Okay. Let's talk about properties of matter. We can have physical properties and we can have chemical properties. What's the key difference between these two? Physical properties are things that do not change the identity or composition of a substance. So if I boil water, it's still going to be water, right? It's just going to be water in the gaseous state instead of the liquid state. Therefore, we can say that definitely, boiling points or melting even is going to be a physical property, okay? Volume is also the same. So whether you have, 20 ml of water, you change that to 30 ml, it's just going to be the same. Nothing is going to change to the composition of water. Malleability and ductility. Malleability is just how malleable something is. This pen right now is not malleable at all, but all these examples right here represent physical properties. Now, chemical properties are properties that once changed, they alter the identity or composition of a substance. So pH change is a very important one. If you have a reaction, and you'll do this maybe in your chemistry lab, where you actually figure out the pH before you run your reaction, and you figure out the pH after you run the reaction. If the pH changes, that's a chemical change. So something within the identity of your reaction changed. Okay. That's a very clear indication that you have a chemical reaction, not a physical change that happened. Release of heat. So let's say you run a reaction, and then your Erlenmeyer flask at the bottom of it is going to be hotter or maybe cooler. Some chemical change has happened. Precipitate. Again, let's say you run a reaction. At the bottom of a beaker, you see a bit of a precipitate or a solid piece that's settled down. That's going to be a very clear indication that you have a chemical reaction. So something happened where you got an identity. I don't want to say change, but I'm going to say that it rearranged, because we know really matter can be created or destroyed, right? So with whatever you have inside your reaction when you start, it's going to rearrange in a way to give you a new product. That's what I mean by a chemical change or chemical property. All right? The last thing I want to talk about is intensive versus extensive properties. If you've been coming to my sessions this semester, I always have cheesy mnemonics. This one is my favorite, probably. So I always say that intensive properties are so intense that they don't need anyone's help. What I mean by that is that intensive properties are properties that do not depend on the amount of substance. They're so intense, get it? Okay, never mind. So these are intensive properties. Examples are like melting point. It doesn't matter how much water you have, water is always going to boil at 100 degrees Celsius, right? Sure, it's going to take longer if you have more water, but that's not the thing we're trying to say here. We're trying to say that the boiling point does not change. That's an intensive property. Temperature, melting point is also another one. All right, let's look at extensive properties. If intensive properties are so intense that they do not depend on the amount, well, extensive properties are going to be the opposite. So they do depend on the amount of substance. So mass and volume are examples of that. All right. Now I want to switch gears and talk about SI unit conversions, significant figures. And for significant figures, we got to talk about addition and subtraction as a unit, and then we're going to talk about multiplication and division as another unit, okay? Because they have slightly different ways of dealing with them. So let me get started with that. This right here, I hope you can see that. Can everyone see this somewhat? I'm going to maybe try to emphasize some of those numbers. Okay. All right. Is this better? Kind of. All right. So this right here is just showing, man. Okay. All right. So this is going to show you how we're going to convert between, let's say I'm giving you something in megaliter and I ask you to go to microliter. This is just a way to help you visualize things. Let's do one real quick. So let's say I give you, I'm going to choose a different thing right here. Let's say I do 5 times 10, or let's do a simple one, okay? We're doing 0.05 megaliter, and we want to go into microliter. If you've been coming to my sessions, the way I do this is I, told my tutees to actually visualize this in their head. And basically what we're doing right now is we're going from the mega right here and traveling all the way to the micro. Okay. If we're moving to the right, which we are right now, I say that you keep the exponent positive. So let me emphasize that using dimensional analysis. I'm going to move that right here. So if I start, and you can do this mentally, of course, but I'm doing it in a way that if you get a difficult number, you have a systematic way of doing it, right? Because obviously you can do this mentally and just move to the right or to the left, right? Move your decimal point. But the way I do it this way is because as you move in your course, you realize that, hey, you're given numbers that you can't really work with visually, all right? So I know it's a simple example, but you can apply this to as difficult as it gets. Okay. I like to put my 1 down. I like to keep it here. So for every 1 megaliter, I'm going to put it's 10 to the something microliter, right? So the something right here, since we move to the right, it's going to be an exponent, of course. Since we move to the right, it's going to be a positive exponent. And it's going to be from 6 to 9. I know it says -9, but we're not going to look at signs. So how many numbers do we need to move from 6, passing through 0, and then go into 9? It's going to be 17 places, right? Make sense? Did I say 17? No, it's not 17. It's 15. Are y'all awake? All right. Okay, so I'm going to keep my exponent positive because I'm moving to the right. Cancel, cancel, and you get your value in, yes? I'm so sorry. That's so true. It's right here in front of me. Yes, we're moving from 6 to 6, and that's going to be passing through 0, so it's going to be 12 places. I did nano, which is -9. Yes. Thank you. If I do something like that, please stop me. But the point is still the same, right? If we move to the right, your exponent is going to be positive. Similarly, if you move to the left, exponent is going to be negative. As long as your 1 is down. I see some people that like to do it differently. They like to put the 10 down here and the 1 up here. That's going to change. That's going to be the opposite of what I just did in terms of negative or positive. Okay. I like to do it this way. I like to put my 1 down. So the 1 that I'm starting with, this is megaliter. I like to keep it as megaliter and just put 1 megaliter. And then that way I can, if I'm going to the right, I can keep the exponent positive here. Okay, that's one thing I want to talk about in terms of SI unit conversions. I know a lot of people struggle with that when they start their chemistry, but I think you guys should be good by now, since you're doing way more complex stuff. But I just wanted to go over it just in case. And if you do have more questions on this, the last 15 minutes, definitely ask me about it, or ask me a specific thing about it. Next thing I want to do is significant figures. So let's start with some basic rules. So I want to say something very specific about zeros. Can you guys see this? Ooh. Okay. I'm going to maybe rewrite this just in case. Okay. I want to talk about the zeros. When you find numbers that are zeros, so if you have a 0, you can have a 0 at the beginning of a number, in the middle of the number, or at the very end. And that's all going to play a very big factor if you consider that 0 as a part of a significant figure or not. So if your 0 is at the beginning of a number, let me give you an example, 0.005, okay? These are not going to be significant. Okay, so any zeros at the beginning of a number are not going to be significant. You're going to start counting your significant number at the very first non-zero number. Okay, that's a very important thing. I know it's very simple, but when you're doing more difficult things in different chapters, you tend to forget these kind of little details. Okay, so you can get a conceptual question on your exam just about, hey, how many sig figs does this have? So in this case, this would have 1 sig fig. Okay, let's talk about if you have a 0 at the middle of the number. So let's say you have a 505. Okay, these zeros are always going to be significant. So this is a non-zero number, so of course it's going to be significant. This 0 is in the middle. It's sandwiched between two other numbers, so we consider that to be significant, and so is the 5. So this is going to be 3 sig figs. Okay. Let's talk about the last case. What if we have a 0 at the very end of a number? Here, you got to be careful. You have two scenarios. Let's say I give you 500. Okay. This is going to be 1 sig fig in this case, if I give you 500. Okay, why? Because we only consider the non-zero numbers as significant. Anything to the right, if it's just a 0, it's non-significant. Okay. What makes them significant is if I put a decimal point at the very end. So if I do this, see this decimal point? This will make my 2 zeros at the very end significant. So this is really 1 sig, and this is 3 sig figs, right? Does this make sense? All right. So let's do just a couple examples. 303.0. How many sig figs do you think this will have? 4, right? So this is 1, this is 2, this is 3. I know we have a 0, but it comes after a decimal. So we can consider that as a sig fig. Okay. So this is in terms of zeros. Let's do a bit of addition, subtraction, sig figs. So this is the rule for addition and subtraction. So let's say I have two numbers, 22.31 plus 8.059. Okay, so for addition and subtraction, the way to do this is looking how many numbers you have past the decimal point. So right now, for this one, I have, two numbers past my decimal. Here, I have 3 numbers past my decimal. Okay. Your final answer will be the addition. Of course, you plug that into your calculator. But the final answer should have 2 numbers past its decimal point, and then you count your sig figs. So let me do this. So if I add this up, I'm going to get, if I just plug this into my calculator, I'm going to get this. Okay. From here, we look at our 2 numbers originally. We know that the least one had 2 numbers past its decimal point. So my number, to be accurate in terms of sig figs, should have 30.3, and it should stop here at the 6. But since we have a 9, it's going to go into a 7. Okay, and this is going to be my final answer. So yes, it has 2 numbers past its decimal point, but in terms of sig figs, how many sig figs are these? They're 4. Okay, are we good on that? This is the rule for addition and subtraction. If you have anything in terms of addition or subtraction, you can apply that. Look at your number that has the lowest number of numbers past its decimal point, and your final answer should have that many numbers past its decimal point, and then you can count sig figs, or basically count them out. Okay? Let's look at the final thing we have, which is multiplication and division. Okay, so let me give you an example right here. Let's say I have 30.0 times 0.050. Okay, when we're doing multiplication and division, it's pretty straightforward. I think, in my opinion, it's more straightforward than addition and subtraction, because what we're doing here is you're going to look at your two numbers again, but you're going to first sure you can multiply them out and find your answer. This would be, you know what? Let's do it one step at a time. So you're going to count how many sig figs this first number has. Okay? How many sig figs do we have here? We have 3 sig figs. What about the second one? How many sig figs? Okay, you may be tempted to say, 1, 2, 3, 4, but we don't count the first zeros at the beginning of the number, so we technically have 2. Okay? So our final answer should have 2 sig figs. That's how we're going to do it. So it's going to be 1.5. Okay, so remember the difference between addition, subtraction, multiplication, and division. Addition and subtraction are going to look at the decimal points, and your final answer will have as many decimal points as the one with the lower decimal points. So going back here, this number had 2, and it's the lowest. This one had 3 numbers. So we're going to pick our final answer is going to have 2 numbers past its decimal point. And we do so here. Okay, and then we count our sig fig. But for multiplication and division, flat out, just look at your sig figs first, and your final answer will have that many sig figs. It's a bit more straightforward in my opinion. All right? All right. I think we're doing well in terms of timing. So let's keep going. So we covered this. I'm going to really quickly go over Dalton's 4 postulates. These are more conceptual questions. You might get something like this on your ACS in terms of just, hey, do you know especially 3 and 4, you got to know these. So I'm going to brush through them real quick. The first one is pretty simple. It just says that all matter are composed of extremely small, indivisible, which means they cannot be broken down any further, particles, and we call these particles atoms. And we all know that. Second postulate is going to be that all atoms of one element are always identical to each other. Okay? The atoms of one element will, however, differ from the atoms of another element. So if you have lithium, the atoms within lithium got to be for lithium. They can't go to any other, element. Very straightforward. We know this now. Back then, these were very extremely important discoveries because they didn't know, about all of these things. The third postulate is what's important for us, and the fourth one, of course. So the third one is really called the law of conservation of mass. Okay. So let's talk about that. Right here, the law of conservation of mass tells us that, we know that atoms cannot be created or destroyed. All they can do is become converted into other types of atoms when we do a chemical reaction. So you remember back when I talked about physical properties and chemical properties just a while ago? I said when you have a chemical property, you can have a precipitate or something like that, pH change, nothing is being created, right? Even though you see a chemical change, nothing is created. What we have is these atoms within your reaction are rearranging in such a way that you get a new product out of it, okay? So it's really a rearrangement of products rather than the creation of something new. So that's really the law of conservation of mass. These atoms are simply rearranged in a way to make new compounds, okay? Let's talk about the fourth postulate. This one has two parts to it. First one is called the law of constant composition. And the second one is called the law of multiple proportions. So this is important for you guys to know. I remember getting a question like that back when I took Chem 1. Constant composition, let's talk about this one. All that means is that compounds are atoms of 2 or more elements. Ooh, my bad. 1 second. Okay, I want to give you an example about that. water. Anywhere in the world will have exactly the same composition. Okay? If you look at water, it's going to have a ratio of 18:1 in terms of grams. And this will always be the case. Okay, wherever you go in the world, if you get a sample of water, it will always have that constant composition. Okay, it's a law that we know now as being very simple, but back then, again, they really had a way of figuring that out and making sure it's accurate. The second one, the law of multiple proportions, and this one I kind of want to have an example about. Okay, this one confused me back in the day when I took Chem 1, but basically, let's look at nitrogen and oxygen. Okay, we have nitrogen and oxygen. What the law of multiple proportions says is that, hey, if I have nitrogen and oxygen, I can make different things out of it. So let's say I want to make products. I can make NO. I can make NO2, right? These are all possibilities that I can make. Sure, I'll have to change the number of moles here, but still I can make them out of nitrogen and oxygen. What this is saying, though, this law is saying that even though that I make, new compounds, somehow, some way, they will have to be what we call multiples of each other. So let me show you how. You look at your periodic table. The molar mass of nitrogen is going to be 14.007 or 14.101, sorry, and oxygen is going to be 16, right? If we do a ratio right here, we have 1 nitrogen and 1 oxygen. So if we do a ratio in terms of oxygen to nitrogen, we're going to just do 16 over 14, right? And this would give us 1.14. And this shows it right here, basically. Okay, so I'm going to rewrite it here. Okay, now let's look what happens when you look at NO2. Again, we have 16, but we have 2 of them, so it's going to be 16 times 2 over 14. And what we get here is 2.28. Okay. Now, this number and this number have something special about them, and that is, if you take this number and multiply it by 2, a whole number, we get 2.28. Okay? This is the law of multiple proportions. It's telling us, hey, when you make new compounds, they're always going to be somehow multiples of, somehow a whole number multiple. Okay? That's why, hence the name, multiple proportions. Okay? So again, just to re-emphasize, ratios will always be multiples that are whole numbers. Okay, this concludes really the easy stuff about chapter 1 and 2. So I think from here on, we're going to speed forward and we're going to do a bit more difficult things. But this is a good start for us, a good warm-up for us. So let's do just a few problems from chapter 1 and 2. And these problems will basically, I think, deal with isotopes. And again, remember, isotopes have different neutron numbers, also different mass numbers, because the mass number is made out of protons plus neutrons. So let's start with the first one, and let's see what we have. Okay. I'm going to keep your paper right here so I can solve with you guys. Okay, so question 1 says a sample of element X contains 100 atoms with a mass of 12 and 10 atoms with the mass of 14. And they want you to calculate the average atomic mass, okay, of the element. Okay. To find the average atomic mass, what you need to know is that you need to know your mass, obviously. but more importantly, you need to know the percent abundance of that specific atom that you have. Okay, so we have two elements right now. I'm going to call them element 1 and 2. Let's talk about element 1. In our question, okay, we have 100 atoms of the first element. Or element, element with mass 12. Okay, the percent abundance of that, we know we have 100 of it. Sorry, 100. Okay, but what is our total? If you look at our total, we have 100 atoms here. The other one has 10 atoms. So we know that our total should be 100 plus 10, which is 110 to start out. So percent abundance is really just going to be how much you have of that element over the total. So we have 100, the total is 110, so we're just going to do that. And that's going to be 0.909. Now if you want it in percentage, you would just time it by 100, right? I'm going to keep it as a decimal right now. Let's do the second one. So mass, we had mass 14. Okay, the other one had a percent abundance. We had, if you remember from the question, we had 10 atoms with mass 14. And we'll address the mass in a second. Right now we're just seeing the percent abundance out of, our 100% element. Okay, we have 10 atoms over 110, 0.0909. So these tell you the abundance that we have of each element. Okay, now we can do the average atomic mass. Remember, the average atomic mass depends on the mass and the percent abundance. Okay, so we're given the masses. The first one is 12, the second one is 14. So let's do this, 12.00 times percent abundance, right? So 0.909, and I usually have it in decimals. This is the best way to go about this to get the question right, which I'm sure you want on an exam. The second one is 14.00, and it had percent abundance, or just an abundance of 0.0909. Are we good? Right? And this will give you the final answer. Your final answer should be 12.18. Okay? I want to give you units in terms of this. This will be AMU, atomic mass unit. I wouldn't stress this too much. I want you to understand the concept of average atomic mass, that it depends on the mass and the percent abundance. Guys, this is how the concept of isotopes, leading up to the mass number on the periodic table, this is exactly how it works. You take all your isotopes, okay? Your isotopes are going to have different mass numbers, and they're going to have different abundances in nature. Some of them are going to be more, some of them are going to be less. And you need to take account. Let's say I have, carbon 14 and carbon 12. Okay, sure, I have both of them as isotopes, but which one is more abundant? This will kind of account for the final average atomic mass. So the periodic table that you're looking at when you're looking at the molar masses, this is not just a molar mass in terms of one element in a way, one isotope. This is all the isotopes in nature. All right. Let's look at the second question. Nitrogen is made out of two isotopes. Okay, nitrogen 14 and nitrogen 15. Want to emphasize when you see a dash like this, so the element symbol, dash, and then a number, this is the mass number. This is not your atomic number. And they're giving you that the atomic weight is 14.007. Now they want you to figure out the abundance of each isotope. Okay? So this is kind of the same concept, you're just working a bit backwards in a way. So let's tackle this one. Okay. So remember, they gave you the atomic weight, and we know this is an average. Okay, we know this is an average. So this is your average atomic weight, in a sense. So I'm going to put this right here. And I'm going to put an equal sign. Okay. We also have the two masses, or the mass numbers. Right? So we can put these here as well. Plus 15. Now we need to account for the percent abundances, or the abundances, which we don't know about. What do we know, though? We know that these are all the abundances are all gonna add up to 100%. Okay. Since we know that, I'm gonna set one of them equal to x as a variable, and the other is gonna be 1 minus x, 1 being 100%. Okay. So next. And from here, it's just algebra, guys, right? So, 14x plus 15 minus 15x. Gonna move that. You can multiply that in. Okay. And I don't want to do the whole math because I have it right here because I don't want to waste your time. But basically what we're doing, and you know, right here I started with the 14, right here I ended with the 14, but it's the same thing. Okay. And this is how we did all the math. You find x, and from there you can just plug into the 1 minus x. Okay. The x is really going to be your element that has the mass 14. That's going to be the percent abundance of that element with the mass number of 14. The 1 minus x is going to be the percent abundance, not the element, sorry, the isotope. It's going to be the percent abundance of isotope that has the mass number of 14. The 1 minus x is going to be the percent abundance of the isotope with the mass 15. Okay? All right, let's move on. True or false question? I think I drilled this enough in your heads, so let's see. The atomic weight of an element is calculated based on the highest isotope abundance of that element. What do you guys think? Is that true or false? All right. I see some head shaking, so it is false. Again, it's based on the average of all the isotopes and their percent abundances. Okay? And then the final one right here is just a conversion, going from microliter to megaliter. I can do that real quick for you. Okay, so this is micro, ooh, what just happened? Microliter times. And again, I said I like to put my 1 down. And then if you use the chart that I just talked about, right here, to go from micro, we're going to mega, we're going to go to the left. Micro is -6, mega is +6, right? So we're going to go to the left. So my exponent is going to be negative. So this is going to be 10 to the -12 megaliter, okay? Some people now don't like to do this at one step. They like to go from, let's say, microliter to liter, and from liter to megaliter. You can do that. As long as you're comfortable, just do what's most comfortable to you, as long as you keep getting the consistent right answer, okay? So this is just going to be 5 times 10 to the negative 2, or 0.05. Same thing. Megaliter, of course. All right? So now let's move on to chapter 3 and chapter 4. So I think from here on I'm going to, actually throughout this whole packet, I kind of group each 2 chapters together. I'll do that with the exception of the last couple of chapters. Now your packets, if you printed them out, they're not comprehensive. I've added a few things that I want to talk about. For example, the gas chapter, I've added some stuff. I've added some stuff about quantum numbers. Do you guys remember that? The principal quantum number, angular, all that good jazz. We're going to talk about that. It's not in your packet, but it's all going to be here, and I'm going to show it on the doc cam. So, I'm going to start speeding through some stuff. So let's get started. This is more going to be reviews from here on in terms of question reviews. It's not going to be conceptual. So we're going to start working with numbers. We're going to start working with problems. Right? So what's the difference between molecular formula and the empirical formula? This is very simple. The empirical formula, this is going to be the simplest form that you can have for a compound. Let me give you an example. C6H8. Okay. Now this is called a molecular formula. This is how the compound right here exists in terms of the numbers of atoms within that compound. So C6H8 is going to have 6 carbons and 8 hydrogens. Okay, but we can technically narrow this down if we divide by 2 or by 2. You need to divide by something that you can get the least. Basically, we're getting your compound in the simplest form. Okay. So this is the simplest form of this compound. This is called the empirical formula. Okay. Question 2. Can 2 compounds with different molecular formulas have the same empirical formula? What do you guys think? Yeah. An example right here is butane and ethane, which you don't need to know the names of, but I just wrote them down for me. You'll learn more about that in Organic 1. Butane looks like this. Ethane is going to look like this. Okay. If we simplify butane, it's going to be C2H4, which is going to be exactly like ethane. Okay. So they're going to have the same empirical formulas, even though they have different molecular formulas. All right. This can be broken down more, of course. This can be C1H2, and this can also be broken down to CH2. Same thing. Technically speaking, this is the empirical formula because this is simpler than this. See what I mean? So you need to get it to the simplest form to call it an empirical formula. All right, so what is the empirical formula of, this is called peroxide or H2O2. Again, we're just getting it to the simplest form. So right here what we have is the molecular, or we might actually not have the molecular, it depends. But to get it to the empirical, it's going to be HO, or H1O1. Okay? Let's move on. We're going to talk about ionic compounds versus molecular compounds. So this is an important concept. Remember, ionic compounds are compounds that are made from a metal plus a non-metal. So I'm going to write that down. Okay. Now, a molecular compound is going to be 2 nonmetals. So non-metal plus non-metal. Okay? The way we name these are going to be different. So right here, this is nonmetal. This is another nonmetal. So this is going to be a molecular. Okay? Molecular. This right here, sodium, it's going to be metal. Oxygen is a nonmetal. How do you know that? Periodic table, guys. Right? Alkali metals, alkali earth metals. Right here, transition metals. So all these are going to be metals. This side is mostly nonmetals, exception aluminum and a few other things that are metalloids. So this is going to be an ionic compound. Okay. Again, calcium is a metal, so this is going to be, and chlorine is a nonmetal, so this is ionic again. SF4 is going to be molecular, because sulfur is a nonmetal and fluorine is a nonmetal. Just for fun, let's name SF4. Okay, the way we name them is different. Anyone know how you'd name this one? Yeah, you use you use these, right? Yep. Now, if it's, what do you think this one will be called?
So SF4 would be
I'm so glad you said that. He said mono sulfur tetrafluoride. Okay, this is so close to being correct, but I'm so glad you said it because it's incorrect. But that's okay. That's okay. I'm so glad because you're not going to do this on your exam. Okay. You do use them. Right? The subscripts down here, you do use them. But if you have a mono on the first atom, you don't use it. Okay? You can use a mono on the second element, but not the first one. So this is really, to be correct, you take out the mono. It's just sulfur tetrafluoride. Okay? Let me give you another quick example just to clarify this. If I had NO, and no, this is not NO, this is the compound NO, right? We have 1 and 1. So this is gonna be nitrogen, not mononitrogen, just nitrogen monoxide. Okay. So you start using the mono, just for the second one. Okay. Good. All right. So let's name Na2O. Right? We said this is ionic. We said that. And we said that we name ionic compounds differently than molecular compounds. Now, for molecular compounds, we use the subscripts to name them, right? For ionic compounds, we don't use the subscripts at all. What you do is you name the metal first, as it is. So what is this? This is sodium, right? So you just write sodium. Okay. And the last thing, right here we have oxygen, but you're going to change the ending to IDE. So it's going to be oxide. Okay, so this is going to be sodium oxide. This naming right here for ionic compounds, where you just name, and again, I'm going to write that. I hope you guys. So for ionic compounds, okay, name metal as is. That's the first step. Second step is name nonmetal. Switch ending to IDE. This is going to be the way you name anything for ionic. So let's do the second example I had here. This one was CaCl2, and we said this is ionic. So what do you guys think this will be called? Calcium. It's chlorine, but we just add this, yep, that's correct. It's going to be chloride. All right? So remember these, remember to keep these straight in your head in terms of molecular versus ionic. For molecular, yes, you can use the subscripts. For ionic, no, you don't use subscripts. You use this method, and it's very consistent with any ionic compound that you have. All right, moving on. Let's talk about this. You gotta know these because you need to know these for balancing chemical equations. You gotta know them for writing a chemical equation if you need to. So these are some of the most important polyatomic ions. If your professor covers some different ones, let me know or ask me about them, and I'll address them. But let's talk about this. Our +1, ammonium, is going to be NH4+. Please do not mix this up with ammonia. Okay? Ammonia is NH3. Do not mix these two things up. Okay? Just for future reference, you'll use this in organic. Ammonium is going to be acidic. Ammonia is going to be slightly basic. Okay? Just throwing that out there. Hydronium is going to be H3O+. Okay, our negative ones. Hydroxide, OH-. Cyanide, CN-. Acetate. Now, acetate is one of those that you have like 3 ways of writing them. So I'm going to write CH3, COOH. Okay. You can also say CH2, C2H3O2. These are all the same thing. Okay. Now, nitrate and nitrite, chlorate and chlorite. As you'll see, we're going to have sulfate, sulfite, carbonate. Oh, these two are, never mind. Okay. These two are very, similar. The ending is 8 here, the ending is I here. Make sure you know these. Okay. Nitrate is going to be NO3-. Nitrite is just going to have one less oxygen. Excuse me. So NO2-. Okay. Chlorate is also going to have a -1 charge. It's going to be ClO3-. Okay. Chlorite is going to have one less oxygen. So again, ClO2-. Okay. I just want to throw it out there that we also have something called perchlorate and hypochlorate. Okay. So note this as your basic one. Chlorate with the 3-. This is your basic one. Okay, this is chlorate. If I tell you perchlorate, just add 1 oxygen. So it's going to be ClO4-. This is perchlorate. Okay. Perchlorate. Okay. Chlorite, we know this is chlorate. Chlorite is going to have 1 less than the chlorate. So this is chlorite. You can also have something called hypochlorite. Hypo just means 1 less oxygen again, so it's going to be ClO-. Okay. Just remember this one, and it's like going up or down the staircase from there. Okay. Notice all we're changing is the subscript. Going +1, -1, and -2 at the end. Okay. Sulfate, sulfite, it's going to have a -2 charge, so it's going to be SO4-2-. And sulfite will have 1 less oxygen, SO3-2-. Phosphate and phosphite going to have 3- charge. I'll come back to this in a second. So it's going to be PO4 3- and PO3 3-. I believe for your course, phosphate is the only one with a 3- charge. So make sure you know that. Okay. make sure you know that it's not a 2 minus. As far as I know, sulfate, sulfite, carbonate, and chromate are the only ones you need as a -2 for this course at least. Okay. What's that? Permanganate. Yeah, that's another one we'll discuss. I didn't discuss this one just because I don't see it in example problems. But I can address that, yeah. Remind me at the, I'm going to write a note about this. At the 15-minute mark, remind me to address maybe 3 or 4 more polyatomic ions that you guys might need, okay? Just for the sake of time, because I don't want this to take more of our time. So we'll come back to that. Where was I? Okay, so carbonate is going to be CO3 minus. Okay, chromate is going to be CrO4 minus. Okay, he asked about permanganate. It's going to be MnO4 minus. Okay. All right, moving on. So name or write the molecular formula for the following 3 molecules or compounds. Okay. This is going to be kind of an ionic compound, but with a polyatomic ion as its anion, right? So it's going to be potassium sulfate. Okay, remember there's a 4. When you see a 4 for the it's sulfate basically. If you see a 3, it's sulfite. Barium oxide. They want you to basically write the molecular formula for this. Okay. Notice for barium hydroxide, there's the ending IDE. So this is indicative that you have an ionic compound, right? So it's going to be barium. What charge does barium have? If you yep, 2+. If you forget, just pull up your periodic table. These are always going to have +1. These are always going to have +2. Okay. These are always going to have -2. Oh, -1, sorry. And then -2. Okay. These are the noble gases. So they don't have a plus or negative. They're just going to be inert. So barium will have 2+. Hydroxide is one of our polyatomic ions. It's going to be O minus, OH minus. Okay. Now remember, you need your charges to cancel. So this will be Ba, OH2. Okay. When you want them to cancel, you can't add ions or anything like that. All you can add is subscripts. Okay. Last one. This is going to be iron chloride, right? Semi, right? You need to remember that iron is one of your transition metals. Anything in the transition metal area, guys, remember you need Roman numerals for them. Okay? So iron, if you remember from class, can be 2+ or 3+. You don't know which one it is right now, like this. You need to specify. So technically speaking, because we know that chlorine is a halogen, all halogens are -1. You have 3 of them. So that means you're going to have -3 sign. So let me do this right here. So let's say we have iron, and here we have chlorine. Each one is negative, but you have 3 of them, so it's going to be -3. Okay? You need the charges to cancel, so this needs to be a +3. Okay? Therefore, this is not just iron chloride, this is iron 3 chloride. Okay, make sure you catch this if you have a transition metal. True or false, CO is called monocarbon monoxide. What do you guys think? False? We don't use the prefix for the first one. Okay, this is just carbon monoxide. All right, moving on. The correct name for Al2O3 is, gotta know this is an ionic compound, so this is really going to be just the metal plus the anion, adding the IDE at the end, so it's going to be aluminum oxide. Okay. Naming acid bases. Okay, this is fun stuff. We have two types of, two categories. We have binary acids and oxyacids, if you guys remember. Binary acids are really just a hydrogen plus anion. And this anion does not have an oxygen in it. Oxyacids are when you have a hydrogen plus anion, and this anion has oxygen. Okay. So going over these, this will be a binary acid because it doesn't have oxygen in it. The way to name these is very easy. Let me give you a quick method. If you have a binary acid, all you do is you write hydro. Okay. And then you name your anion, but it will have an ending of ic, ic, and then acid, okay? So this is hydro, this is chlorine, but it's gonna become chloric, and you just add the name acid, okay? So for any binary acid, an acid that does not have an oxygen, you can use this naming system. Okay, so this is gonna be hydrochloric acid. What about this one? Again, it's a binary acid, right? So it'll be hydro, sulfuric acid. There we go. Okay. Let's look at the third one. The third one is an oxyacid. Oxyacid meaning it has an oxygen in it. Okay. For these ones, you don't use the naming system of binary acids. For oxyacids, what you do is you just name the polyatomic ion. Okay. With kind of a tweak to it, if the atomic ion ends with an 8, okay, it becomes ic acid at the end. If it ends with an 8, it becomes us acid. Okay. I have a quick mnemonic for that. We ate, it's cheesy, but it sticks. So we ate something icky, but it's I with us. Okay? So A becomes ick, I becomes us, or OUS. Okay? So if I have H2SO4 versus, let's say, HNO2, okay? You guys got to know that this right here is a polyatomic ion. You also have to know that this is an oxyacid. Therefore, we're not going to use the naming system of binary acids. We're going to use oxyacid naming, which basically says, hey, just name your polyatomic ion. If it's A, it becomes ic acid. If it's I, it becomes us acid. So this is going to be sulfuric acid. Okay? This one right here, this is, what do you guys think? Is this nitrate or nitrite? This is nitrite. So this will become nitrous acid. Okay? Moving on. And I'm going to try to speed through because I'm a bit behind, as I'm kind of noticing now. Let's do this. There are how many atoms of sulfur in 25 molecules of this? Okay. This is where you start doing dimensional analysis stuff. So let's start here. You have 25, always start with what you have, obviously, right? So you have 25 molecules of C4H4S2, okay? Now for every one molecule, for every one, okay, how many are you gonna have? So I'm gonna write this, for every one C4H4S2, how many sulfurs do you have? Okay, how many atoms of sulfur? You're gonna have 2. Okay, so this cancels, and it gives us 50. Cool. And yeah, this was the answer. Okay. Mass percent of carbon, rounded to 3 sig figs. I'm going to skip this one just because of time. I want to cover the more in-depth stuff like calorimetry and all of that. So I'm going to actually, I'm looking at the time right now. Yeah, I'm definitely skipping this, okay? I'm going to address number 13, though. It's going to be important. Empirical formula versus molecular formula problems. So you know the concepts behind it. We talked about empirical being the most simplified, right? And molecular just being the one that, is like what the atom is, how many atoms you have. So I want to do this problem specifically. This problem is asking you to do, and we have a few others here too. Okay, gonna skip this as well. We'll come back to, just for time's sake, guys. All right. So more stuff for chapter 3 and 4. We're going to jump into the more problem-based things, of course. So let's start with the first one. You have a 0.15 gram sample of solid lead 2 nitrate. First of all, you got to know how this is written, right? So lead 2 nitrate is going to be PbNO3 2. Make sure you switch everything into liters. So this is going to be 0.125 liters, right? Okay, they give you a reaction right here. Assume no change in volume. Chemical reaction that takes place is represented with the following equation. They want you to identify the limiting reagent. This is definitely going to be a problem on your final. Okay, so how do we do this? The way to do limiting reagents is finding out their moles. Okay, so you can pick whatever you want in terms of comparing moles. What I'm going to pick for this problem is I'm going to see this one, NaI. Okay, so let's start. So let's see how much this lead nitrate, how much will it make how much in moles would it make? Okay, so let's start there. So if I do PbNO3 2, we were given that we have 0.15 grams of it, right? Using its molar mass from the periodic table. For time's sake, I'm just going to write it. And it's going to be 1 mole of lead nitrate. But we want to see how much it can make from this, okay? Or how much it can make in AI. Here you use the chemical equation. For every 1 mole of lead nitrate, lead 2 nitrate, you're going to make 2 moles of NaI. So I'm going to say for every 1 mole is going to be everything cancels and we have things in moles of NaI. And this is going to be 9.005 times 10 to the negative 4 mole of NaI. Okay. Now notice the problem gives you the molarity of sodium iodide, which is NaI. Okay? So from molarity, you know you can get to moles if you use the volume. So sodium iodide, or NaI, we have 0.1 molar, right? Which is also saying over mole over liter. And we also have the volume given to us. So we can just multiply the volume, guys, to get the moles of it. Okay? So which one makes less sodium iodide? It's this one, isn't it? Oops. It's this one. Okay? Therefore, this is our limiting reagent because it makes less sodium iodide. You can do this for anything as long as you're consistent. So I could have done this for something else, but given the information in this problem, the easiest thing to do was for sodium iodide. So limiting reactant is sodium iodide, and then we have to calculate the molar concentration of nitrate. Okay, so this is the important part because part B relates to part A. You can't solve this unless you use the limiting reagent. Okay, don't go ahead and use the excess. This is going to be an excess. So technically in the reaction, this is going to run out first for this. So you can't use this for your problem from now on. You've got to use your limiting reagent. Okay, so for part B of the problem, we're going to start off with what we have as a limiting reagent. Okay, so I'm going to start with 0.15 grams, or I could have used the moles, but I'm going to start all the way over. I'm going to start with my limiting reactant, and I'm going to do dimensional analysis. Okay, molar mass now again go to your equation. For every 1 mole of it, okay, you're going to have 2 moles of NaNO3. And this is what we want, guys. The question is asking us for the NO3. So, just for time's sake, this is how I did it. And this will be your answer, 7.25 times 10 to the negative 3 molar. Okay? All right. This is an important one, so make sure you know limiting reagent, excess reagent. Make sure how to do calculations. Remember to use stoichiometry. Stoichiometry needs a balanced equation, guys. Okay? You can't use stoichiometry without a balanced equation. So make sure your equation is balanced. As far as I know, both professors like to give balanced equations. So Hyder and Patino, Dr. Patino and Dr. Hyder always give balanced equation. If they don't, make sure you check. It doesn't hurt. Just check that roughly everything is the same, and then start your problem. Okay, Number 2. So it's asking if this dissolves in water. This is iron 3. No. Iron 2 nitrate. If it dissolves in water, what are the particles in solution? Okay. You got to know how things dissociate. This is ionic, so it's going to dissociate into its ions. So it's going to be, we see a 2 here for the NO3. We know that nitrate has a -1, but we have 2 of them, right? This means that our iron must have a +2 charge. So it's going to have a +2. And we're going to have 2 ions of NO3, 1-. So these are going to be our 2 ions. Okay? Moving on. With which of the following will ammonium ion form an insoluble salt? So you got to know a bit of solubility rules here. Ammonium is NH4+. Okay? With which will it form an insoluble salt? Okay? If you know solubility rules, you know that ammonium is always soluble, right? So the answer is none of the above. I believe Dr. Patino provides a solubility chart for you guys. For Dr. Hyder, I doubt she does, but check with her. Okay? If she doesn't, then you have to memorize some things that I won't cover today. Which of the following is not a strong acid? Okay? We learned 7 strong acids. You got to know them, guys. ACl, HBr, HI, H2SO4, HClO4, HClO3, and HNO3. These are our 7 strong acids. Okay. Cut straight to the point. HF is not. Question? You good? Yeah? You sure? Okay. So HF, anything that is not strong is weak. For our purposes, this is how we're going to roll in Chem 2045. Okay. So, noticing that I'm picking the pace here, and I'm going to keep doing that until the end, because we only have almost an hour left. So let's keep moving. How many moles of potassium ions, notice it's ions, are present when you have 343 milliliters of a solution that is 1.27 molar? Okay, make sure you switch everything into liters. So this is 0.43 liters. 343 liter. Okay. This is a simple, molar to mole conversion, right? So 1.27 mole over liter, because we know molarity is always mole over liter. Okay. You do your calculation, and you get 0.435 mole. This is a tricky part about this question. This is mole of what? This is mole of K3PO4, guys. Okay? This is not what the question is asking for. The question is asking for potassium ions. Okay? So you have one more step to take. How many ions do you have within your molecule, within your compound? You have, for every one, right? For every one of this, you have 3 K+ ions. So really, you have to take this and you got to continue it. For every 1 mole of it, you have 3 moles of ions. And your answer will be this. For time's sake, let me check the answer. My key. It's going to be 1.31. All right? So make sure you know how to do molarity to moles, but also make sure you read the question. Is it talking about ions? Is it talking about moles of compound? What exactly is it talking about? Okay? Because you can always use stoichiometry. And if it's an ion, you need to look at the subscripts per 1 mole of that compound. Okay? All right, I'm going to skip a few here. The total concentration of ions for HCl. Okay, HCl is a strong acid. Strong acids dissociate completely. So you're going to have two ions, H and Cl. Okay, so your answer is going to be 2 times this. It's going to be D. Let's move on to 7. Net ionic equations. This is important. Okay, they didn't give you the equation, but you have to write it out. So you have HF plus KOH, and you have to predict the products. And this is what we call a double replacement reaction. What I mean by that is that you take the cation, and you take, it steals the anion of the other compound. Vice versa here. Cation steals the anion of the other compound. I just realized the color match is very horrible. There we go. Okay. So it will become HOH, aka H2O, right? Plus KF. The trick to this is to know whether you have solid, liquid, or gas. Now they told you that things were aqueous here. So these are all aqueous. Okay. Water is water. It's always going to be liquid. The question is KF, is potassium fluoride solid, liquid, or gas? You need to know that in order to do your ionic equation. Okay. KF, if you look at your solubility rules, it's going to be aqueous. Okay. Why? Because simply stated, alkali metals are all going to be soluble. Anything that has an alkali metal in it is soluble. Okay. So it's going to be aqueous. What that means is this is going to dissociate into its ions. So if I write this down, and let me do this again for time's sake, guys. I want to show you the answer key right here. Okay. So we started with this, wrote everything down, and we found out that this is aqueous. So I can dissociate only the aqueous stuff to make my ionic equation. Liquids do not dissociate, solids do not dissociate. Okay? So, bam, we have this. Then you cancel out everything that needs to be canceled. Okay? Notice, for example, fluorine ion cannot cancel because this is not ionized. Okay? Now you may be asking me, hey, why didn't HF ionize? They gave it to you that it was aqueous in the problem, right? So this is one of the things that you have to know, that HF is a weak acid. Weak acids do not dissociate completely. Okay? Weak acids by definition are acids that dissociate less than 5%. So this is more so than not will be as HF rather than H ions and F minus ions. Okay, this is why we did not dissociate the HF. Okay. Some professors will actually not go in that much in depth, and they'll just assume that the HF dissociates and will be aqueous, and then you can write your ionic equation. So make sure you pay attention to how your professor likes, stuff done. Okay, moving on. Gonna skip this one. This is just solubility rules. Make sure you know this. Just again for time's sake, I'm gonna skip 9 as well. Okay. This is an important one. They want you to know the spectator ions. Spectator ions are the stuff that do ionize in an ionic equation. So again, we have aqueous perchloric acid. If you remember, perchloric acid will be this HClO4. Barium hydroxide, an ionic compound, will be BaOH2. Okay, so you got to write this out. And basically what we do is we're going to write the whole equation out. We're going to see how the products go, and if they're, aqueous, solid, or gas. Again, a double replacement reaction happens, right? Okay. We find out that BaClO4 okay, this is a better view for you guys. I balanced the equation. You got to balance the equation when you're doing the ionic equations. So first what I did, let's take this back. Okay. First what I did here is I just wrote the products. Okay. After I write the products, then I can balance my equation, which this is what I'm showing you here, the balanced equation. Okay. After that, you determine if this is going to be aqueous, solid, or gas, or whatever. In this case, chlorate, as a part of your solubility rules, chlorate and perchlorate are going to always be soluble. So this is going to be aqueous. Okay. Actually, nitrate is also going to be always soluble. Acetate is also going to be always soluble. Pay attention to hydroxide. It won't be, it's not always soluble. It has some exceptions. So make sure you know these. And again, I won't be covering these today for time's sake. Okay, so I cancel out, I ionize things, and the answer to this question is going to be B. I want to show this one more time. Only these will cancel out, so these are the spectators. The spectators are the ones that cancel out. Okay. I think I'll move on to the next chapters now. We're moving on to chapters 6 and 7. Remember, the answer key for everything is found here for the previous stuff that we did, just in case you need the answers. Okay, chapter 6 and 7. Now we move on to thermochemistry. We move on to some thermodynamics and stuff like that. So, question 1. The value for delta E of the for the system performs this amount of work on its surrounding, and it loses this amount of heat. Okay, they want you to find this delta E. Got to remember, guys, that E equals Q plus W. Okay. Now, what I want you guys to remember also is that the values are going to be either positive or negative, and you need to know that. Now, everything will always be given in Chem 1, even in Chem 2, it's going to be given in terms of the system. So notice, the system performs work. Okay? Performs this amount of work. For a system to do work, the W will be negative. And it also loses this amount of heat. Again, things are in terms of the system. So if it loses heat, Q is also going to be negative. Okay, so what does that mean? I have a negative 79 and I have a negative 213. If you add those up, your answer should be negative. And it's going to be negative 92. Okay. We good on that? Now, what if I said work was done on the system? It's positive. Where was the, what did work on the system? The surrounding. Everything is determined between system and surrounding, right? So if work was done on the system, that means that the system didn't do any work. That means that something else did work. So we can say that the work is positive. But this is not so here. We had a negative value. All right. Tracking ourselves. We do have, all right, I think we're in decent shape. I'm gonna, I'm still gonna go a bit in terms of skipping stuff. So if you see me skipping stuff, it's just because of time. Okay. So. Question 2, the value for the delta H, the enthalpy for the reaction, so this is enthalpy, is negative 72 kilojoules. They want you to find the kilojoules of heat, and remember, heat is Q, that is released when 1 mole of HBr is formed in this reaction. So, I want to give you some information. The key to this problem is that you always use the mole-to-mole ratios. Okay, you need to use somewhat stoichiometric values. So what do I mean by that? Let's check it out. So, my delta H, and this is problem 2. My delta H is negative 72 kilojoules, okay? And we can apply the mole ratio in the balanced equation, okay? Notice we have a balanced equation right here. So we can say that this negative 72 kilojoules is released for 1 mole of hydrogen. It's also released for 1 mole of bromide or bromine, and it's also released for 2 moles of HBr. Okay, so whatever value they give you, you can use these molar ratios right here in accordance to that. Right now they want you to look it up for HBr, and they told you that 1 mole of HBr is formed in this. They told you when 1 mole of HBr is formed in the reaction. But the mole-to-mole ratio technically is 2 moles. Okay, so technically speaking, we can say, we can start with negative 72 kilojoules, okay, are going to be for 2 moles of HBr. You can say that because you have a balanced equation. Okay, but they wanted it for 1 mole. So what do you think it will be for 1 mole? Right? What do you guys think? C, it would be half of that. If it's negative 72 kilojoules for 2 moles, what is it? Right? Negative 72 kilojoules for 2 moles. What is it going to be for 1 mole? Half. Okay. Why isn't it not negative? Just because they told you it was released. If they didn't tell you it was released, yeah, you can put the negative. All right. Let's do this one. The value of delta H for the reaction below. This is for the whole reaction. Okay, so you can use the molar ratios again. The amount of heat that is released by the reaction of 25 grams of this with water gives this amount of heat. So let's start with what we have again. Okay. You use the molar mass because you want to switch to 1 mole of Na2O2. But remember, you have 2 moles of it here. So technically, for every 2 moles of it, you get the negative 126 kilojoules. Okay, so you run this and it should be negative 20.2. Now they said released, so you don't have to add the negative in your answer because they gave it to you. Released means negative. All right. All right, now I want to do a bit of calorimetry. So I want to talk about the different types of calorimetry. We have 2 types that I want to talk about. We have, in this semester, during your semester, we studied about constant pressure calorimetry, but you didn't study it that way. You learned it as, you know, the coffee cup calorimetry. That's probably the term you guys used in class, right? Which is really a type of calorimetry that uses constant pressure. Okay, so these 2 terms are synonymous. It could be called a calorimeter, it could be called a coffee cup calorimeter, or it could be called a constant pressure calorimeter. That's the first type. This is actually the type that we use Q equals MCAT for. Okay. The second type is called bomb calorimetry, or just a bomb calorimeter. And this is the type where we use the Q equals CAT equation. Okay. Now again, when you're talking about thermochemistry or anything in terms of heat, you need to know, hey, am I dealing with the system or the surrounding? Okay. So for a coffee cup, the Q, the heat, is going to be for the surrounding. Whereas for the bomb, nah, just kidding. For the bomb, it's also going to be the surrounding. Okay. They might ask you a question, and you might get this question right, but you might get your sign wrong. That will mess the whole thing up. So make sure that you know these 2 equations give you the value in terms of surrounding, but if they ask you for the system, then you need to flip your answer's sign. If it's positive, negative, negative, positive. Okay. So let's do a problem. Going to do problem 4. Yeah, we did 3. Okay. You have a sample of aluminum metal, and it absorbs this amount of heat in joules. And then the temperature increases. So I'm going to start writing what I have. Delta T. Remember, when you have delta, it's always final minus initial, right? So our final is this. So 30.5 minus 23.2. Oh, yeah. 7.3 Celsius. Okay. They also gave me the specific heat of aluminum, C. Q is given, of course, the first thing was 9.86 joules. Okay, they want you to find the mass. Pretty straightforward. Q equals MCAT. Right? Now notice, they tell you that the sample absorbs this amount of heat. So will my Q be positive or negative? If it absorbs, it's going to be positive. If it releases, it's going to be negative. Okay? And you got to rearrange this because you're trying to find the mass. But remember, this is in terms of the surrounding. So if my Q of system absorbs is positive, because they gave it to you here, they told you that the aluminum, which is your system, is going to absorb this amount of heat. This means that the Q of surroundings will lose that heat. It's always positive. It's always the opposite. So Q of system is negative Q of surrounding. Okay, this means we need to change this equation and put a negative sign right here to make this correct. Now we can find our mass. And I'm gonna, rearrange the equation. This equation will be negative QC delta T. Okay. After this is just plug and chug. The answer should be 1.5. All right. I'm going to skip. All right. Enthalpy stuff. This is fun. Okay. They want you to find the enthalpy of the reaction. So basically what they're doing is they're giving you two reactions and they want you to find a final equation from these two equations. So we have to make a new equation. We have to rearrange these two equations to make this third equation. Okay? So the way we're going to do that is, let's start simple. Let's write the equation we need to get. This is the... Yeah, man.
I'm sorry. You see a sticky note over here? Like a clump of sticky note?
No. No, man. Yeah. Yeah, let's talk about that real quick. So, do you guys know the conversion from Celsius to Kelvin? 0.15, right? The difference between them is exactly the same. Even though, so, if I have 5, I'm not going to write here, I'm going to write it here. So if I have 5 Celsius or 10 Celsius, the difference is going to be 10 minus 5, which is 5, right? But if I want to switch it to Kelvin, it's going to be 5 plus 273, and then 273 plus 10. The difference will also be, if you do the math, the difference will also be 5. So both of them will have the same difference, whether it's Celsius or Kelvin. You need to remember that. And I kind of skipped over that because I assumed you guys knew that. But thanks for the question. It's important. Okay. So this is the final equation we need. Let's find how we can, rearrange these two equations to find this last equation. So what do you guys think? We see there's a 2SO3 on the right, and we also have that on the final, equation. So we're not going to mess around with this equation. We're not going to flip it. We're not going to multiply it. We're going to keep this the same. This is all happy. But this one, we notice that the SO2 is on the right side, whereas in the final, reaction or the equation, it's on the left side. So we can just flip this equation to the opposite, right? So if we flip this equation, we need to also flip the sign of this. I'm going to illustrate that. Here, I'm going to keep the first equation the same. Second equation I'm going to flip, so it's going to be SO2 going to S plus O2, okay? But I also flip the sign, so it's going to be plus 297. Okay? And now, delta H of reaction is products minus reactants. Oh, my bad. No. Delta H of reaction is going to be the sum of these two. Okay? It's going to be, the individual steps, which are these two steps. We're just going to add them up. So it's going to be negative 790 plus 297. And this should be, I used the wrong values here, didn't I? No, they're right. Yeah, they're right. What I should have done also, by the way, I just realized this. I should have balanced the equation. If you looked at that, right? I should have balanced this by multiplying this by 2. If I multiply this by 2, I need to multiply this by 2. Now you can do the addition. Your answer should be negative 196 kilojoules. Okay. All right. I'm going to skip around a few. We only have around 15 more minutes. So I want to talk about a bit of periodic trends. I want to talk about gas equation for the manometer or manometer. Okay? And I want to talk about the quantum numbers just to finish up. And then I'll give you guys around 15 minutes of just question time. Okay? Does this end at 11:30? Really? How did I, man? No, I knew it, it just my brain didn't. We have like 3 minutes left. All right. Questions, because we only have 3 minutes, so. Yes. This document? Online. So the WordPress site, UCF Study Union WordPress. I listed this.
Is it under the
No, it's under the well, if you go on the Study Union WordPress, it's actually going to be under the chemistry. Then once you go into the chemistry, you're going to see my name, Sam Abad, and you're going to see the files. Okay. And guys, I didn't leave much time for questions because I apparently ran half an hour. Oh, man. All right. So any more questions before we leave? Specific questions about gases or anything like that?
What type of thermal equation do we use? Delta H equals products minus reactants?
Delta H equals what?
Delta H equals product minus reactant. What type of equation do we use that?
Can use that for Hess's law. Yeah. And you can use that for, you can also use products, so final minus initial. Doesn't have to be products minus reactants. Okay? So anytime they don't give you enough values, they only give you the beginning and the end, you can use